In this chapter, we're going to be talking about sequences in series. A sequence is an ordered list of terms in which they follow a particular pattern. For example, my first pattern, I just add 3 to get to the next term. My second pattern, I'm doubling to get to the next term. The third pattern, I am adding 1 to the previous difference to get to the next term. And finally, this last one, a little more difficult to see, but I'm basically adding the previous 2 terms to get to the next one. 6 and 9 is 15, 9 and 15 is 24. We are going to now look at arithmetic sequences. An arithmetic sequence is based on an addition pattern only. The difference between consecutive terms is constant. You can see above there is only one of these that follows that rule. The constant difference is 3. This is an addition pattern, but it does not have a constant difference. So looking down here at this particular arithmetic sequence, we can see that we are adding 4 every time to get to the next terms. The t of 1 equals 7, t of 2 equals 11 is just notation for how we write term 2, term 3, etc., where 1, 2, and 3 easily identify the position of the term. Position 3 is 15. T of n is general term. I don't know what position we're talking about. It's the term in the nth position. So this is our general term. If you ever see that, we don't know n, but we do know that the sequence starts with 7 and adds 4. If I gave you this sequence and asked you to find the 20th term, could you do it? Yeah, you could just keep adding 4 until you get there. But in math, we like shortcuts. Can we find a shortcut to get to that 20th position? Well, let's just focus on these 4 first. How did we get to this 4th position? We added the same number. How many times to get to the 4th position? We added 4, 4, 4. We added 4 3 times to the 7 to get to the 19. So basically, you want to add your common difference 1 less than the term position. So if I want to get to the 20th term, I want to add 4 19 times to my first term. And when I plug that in, 4 times 19 plus my 7, I'm going to get the term in the 20th position without having to add 4 until I get there. So how would I do it here with the 64th position, the term 64? Well, I want to add the common difference of 13. I want to add it 63 times, and I'm going to add that to 47, and that's going to give me the 64th term. That gives me this formula, my T of n formula. T of n is the first term plus 1 less than the term position, n, multiplied by the common difference. And the order of operations doesn't matter for multiplication, or the order doesn't matter for multiplication here. I usually use the second one, but it doesn't really matter. So using this formula, how would we find the 27th term? Well, T of 27 is the first term plus the common difference. What is the common difference here? You notice something different? Oh yeah. We're getting smaller each time, so my common difference is -6. I don't say we're subtracting 6 because the pattern has to be an addition pattern, so I say I'm adding a negative. So that means my common difference is negative. And since I'm finding the 27th term, I'm adding that common difference 26 times, or n minus 1 is 26. I plug that into my calculator, making sure order of operations come first, and I get -136. Write an expression for T of n. We call this the general term. We talked about that before. it is going to be an expression for calculating the term in a term in the sequence for this particular sequence. Because with this particular sequence, t of n will always have a being 20, it doesn't matter what term I find, and it will always have my common difference being -6. For whatever n I'm using, I just don't know n at this point. So I could leave it there, but in math we like to simplify our expressions by getting rid of brackets, using our distributive law, remember negative times negative is positive, and collecting like terms. So there we go. We have our general term. Now if I wanted to find t of 27, I could also use this and just plug 27 in there and go 26 minus 6 times 27. I would get the same answer as up here. How would I find the general term for this one? Let's just practice one more time. I have my first term, my common difference is -5, and I don't know n minus 1. I don't know n, so I write it like that. I could write plus negative or just subtract. It doesn't matter. The key is remembering that when you're multiplying that 5 in, that negative goes with it, and I get -5n plus 5. Collecting like terms, we get 22 minus 5n, and there's my general term. It's as far as I can go because I don't know n. If I knew n, I would go farther. Now let's find some missing terms in a sequence. If I give you two terms right beside each other, you can just take one term, subtract the previous term to find the common difference. In this case, 9. And then if you want to go the other direction, well, you would just subtract 9 each time, and you could fill in the rest of the sequence. That should be no problem right there. But what happens when my terms are not right beside each other? How can I figure out that common difference? What am I adding every time? Well, I know I'm adding 6 once, right? Because 14 minus 8 is 6, but that's once. How many times am I really adding my common difference to get from 8 to 14? Well, I add it once to get there. Remember, since it's an arithmetic sequence, I'm adding the exact same number every single time. So once, twice, 3 times. I need to divide that one jump of 6 into 3 smaller additions, and they all have to be identical. So my common difference is going to be 6 divided by 3, which is 2. I'm adding 2 each and every time. Now I can fill it in. Moving the other direction, I'd be subtracting 2, and there you go. When you're finding missing terms between 2 in an arithmetic sequence, we call those the arithmetic means of the sequence. Alright, so what do you think if I'm missing 3 terms? What's happening here? Well, if you're missing 3 terms, you're adding the same number 1, 2, 3, 4 times. The number of times you're adding your common difference is always going to be 1 more than the number of missing terms. That's where the 4 comes from. And then you take your 22 minus 12 to find out what it is in one jump, and you get 10 divided by 4. In this case, it's 2.5. It's okay to have decimals in your terms. Your n just will never be decimals, right? Because n will always be first term, second term, third term, etc. They'll be your counting numbers. So by adding that, you can fill in the missing pieces once you have your common difference. Another little point to notice, if that's my first term and that's my 5th term, the position of each term, what is 5 minus 1? Oh, that's also 4. So another way you can find the number of additions of D is to subtract the positions. Okay? Don't forget, you could also do that, 5 minus 1 giving you 4. Now that I know that you're adding the common difference 4 times, I also could subtract 1 and know, oh, I'm missing 3 numbers between the position of 1 and 5. So let's try our very last example using all those little shortcuts as best that we can. So here's t of 9 and here's t of 15. So that tells me the 15th position And the ninth position, I should be adding my common difference, 15 minus 9, which is 6 times. I take my 118, subtract my 76, and I punch that into my calculator, and I get 7. So now I know I'm adding 7 every time. Now, I got my first answer, my common difference. Now, I don't want to fill in all the missing pieces. They ask for the ninth, or the first term. I have the ninth term. Well, let's use our shortcut again. I don't know the first term. I do know the ninth term is 76. If I'm, this time, moving this direction, subtracting 7, how many times am I subtracting 7 from the ninth position to the first position? Same idea. 9 minus 1 is 8. I'm subtracting 7, because I'm moving the opposite direction, 8 times. And I'm subtracting it from 76. So my first term is going to be 76 minus 56, which is going to be 20. So T of 1 is 20.